Hi, this is Professor Fernandez. Let's work on class notes B in lesson 15. So if you've watched the previous video, then you saw an example of how we find solutions, vector value solutions, to systems of the form x dot equals ax. What I want to do in this video is I'm going to scroll up here, review these theorems, and connect them together with what we've already learned in the class about linear algebra, specifically linear independence, span, bases of vector spaces. To get us to a point where we can write down the general solution of these SN fold systems. So what are we going to do to combine things here? Well, let's suppose that I have excuse me, a bunch of solutions of this form that and here, suppose I have n solutions of this form that I have found through the method, for example, that we talked about in the previous video. And I want to somehow combine these to form the general solution. I would like to say that the general solution is the linear combination of all of these. Right? That's normally what we do when we find solutions in this class. For some time now, our instinct has been to take the linear combination of them and hope that that's the general solution. And we have all sorts of theorems that have told us that that's true. So this is exactly what we're going to talk about in this new setting of solving x dot equals ax. So how do we do that? Well, in order for this to in fact be the general solution, right, then these have to be a basis for the vector space of solutions. So there's a lot that we need to know, right? We already know that the set V of solutions to x dot equals ax forms a vector space. Okay, so we talked about that in a previous video a few lessons ago. So is a vector space. Great. So now we want to find a basis for it. Well, suppose we have found n of these solutions where n equals the dimension of V. All right. Remember that here I'm assuming that A is an n by n matrix. All right. Then we can think back to a theorem that we had discussed earlier in the course in the linear algebra unit that says if you find n linearly independent elements in an n dimensional vector space, they span the space. Right? Remember that theorem? And I give the reference above, in the previous page in this lesson notes. So if they are linearly independent and span the space, so they are a basis. All right, so we're developing a nice little procedure here. Notice that we already know this, that the set of solutions to x dot equals ax forms a vector space. What do we have to do to use this procedure to show that really this is what the general solution looks like? Well, we got to find n solutions where n matches the size of the matrix, the dimension of the space V, same thing. So we got to do that, and we also have to show that they're linearly independent. So this is where this handy theorem, additional theorem, comes in. So linearly independent. So let me scroll up and show you what that theorem says. I'm trying to scroll up here with, oops, so I'll just do this. Make it easier to scroll. Great. This is the theorem that I'm referring to. So what does this theorem say? Suppose I have k solutions to x dot equals ax. Great. Pick your favorite t sub 0. Why can I say that? Why don't you have to pick specific t sub 0s? Because of this theorem, which says that if you pick an initial condition, there always exists a unique solution to x dot equals ax. And it's defined for all t. Okay, so we can pick our favorite t sub 0. There will always be a solution to this system. Okay, pick your favorite t sub 0. What do you do with it? Then we have this statement. All right, so the part of the statement that we are going to use in our procedure here to find the general solution of x dot equals ax is from this part going to this part, right? This is an if and only if statement, which means that you can go both ways. If this, then that, and also if this, then that, right? These are both true for this theorem. So we're going to use the theorem going the other way. We're going to say, great, if I find a bunch of solutions and I just plug in my favorite t-value, usually it's going to be t equals 0. When I plug that into a vector-valued function, remember when we first talked about vector-valued functions, I explained that when you plug in a t-value, what you get is a vector, right? That's why they're called vector-valued. The values that you get when you plug in a t-value are vectors, not numbers. So if I plug in a t sub 0 into these vector-valued functions, I get a bunch of vectors. And what this theorem then tells me is that if those vectors are linearly independent, then the vector-valued solutions, with the t still in them, are linearly independent vector-valued solutions. So I'm going to scroll back down to where we are then in our procedure. And I'm going to say, great, so in order for us to show that these n vector-valued solutions are linearly independent, we just have to select a convenient t sub 0. And I'm going to say usually t sub 0 equals 0 is the easiest choice. And show that when you substitute it into the solutions that you have, is the vectors that you get, you want to show that this is a linearly independent set of vectors. That completes the argument, right? If you do that, then by the previous theorem, those n linearly independent elements are linearly independent vectors imply that the vector-valued functions they came from are linearly independent solutions. And then you have n linearly independent elements in an n-dimensional vector space, so they are a basis. And basis means, in part, span, which tells us that every element of the space can be written as a linear combination of those n elements. So we are going to use this argument a lot in the rest of the course and the rest of this lesson. So I'm just going to scroll down here, and I'm repeating what I said up here. So I'm going to scroll down here and just remind you that this argument leaves just two things for us to check, and that's what I wrote here. We want to check, assuming, of course, that we have found n solutions, where n is the same as the dimension of the space, which for us is going to be the same as the number of ODEs in the system or the size of the matrix A. They're all equivalent. So assuming we found those same number of solutions, we want to plug in our favorite t-value, again, usually 0. You'll see that in the next video. And we want to show that the vectors we get are linearly independent. If that's true, and if there are as many vectors as the dimension of the vector space, then the argument that we just developed up here kicks in and shows that indeed these n solutions that we found form a basis. So this is going to be a video that I will mention that we'll be coming back to earlier and earlier. I'll keep saying things like, remember from the argument that we developed in class notes B of lesson 15, right? So I'll keep coming back to this video.